evening. So in today's session, I will give the overview of the week 6 lectures. Sorry, week 7 lectures. So in the week 6 lectures, we studied about up to the grain refinement method by dislocation pileup at the grain boundaries. So in today's lecture we will study the two more mechanism that will help in the grain refinement because of the dislocation and grain boundaries. So in the second method, it says that the dislocation density and the effect of grain size on the dislocation density. Density rho. So this method says that the grain boundaries itself act as the dislocation source, because we can see that the grain boundaries are the region between two grains which has the higher most misorientation in the grain boundary region. So many dislocations present on the grain boundaries, so the grain boundaries also can act as the dislocation source. So this method was given by the J.C.M. Lee, and the dislocation density is directly proportional to grain size. So we will derive the hole patch relation using this mechanism. So the hole patch relation which is related to the dislocation density can be written as sigma equals to sigma I plus alpha GB square root of rho. So from the grain boundary and dislocation density perspective, if we assume a grain of size D, then one parameter is defined as the dislocation efficiency of grain boundaries to generate the dislocation. So M can be written as the efficiency of grain boundaries to emit dislocations. And it can also be written as the length of dislocation emitted per unit area. At grain boundary during yielding. So the total surface area of this grain will be 6D square and the total length of dislocation emitted by a grain boundary. Is written as half 6d square multiplied by m. So it will be the 3d square m. So the dislocation density can be written as the dislocation length per volume, per unit volume. So the dislocation length is the 3d square m divided by the total volume of the grain. So that will be d cube. So from this relation, the dislocation density will be 3m by d. If we put this term into the Hall pitch relation term, that is sigma equals to sigma I plus alpha g b square root of 3m by d. So by rearranging this equation, so this term can be written as the constant k. This is how we can get the Hall pitch relation related from the dislocation generating by the grain boundaries. One more method is that the work hardening theory. So by the work hardening theory, we can say that the distance traveled by a dislocation in a grain is equal to the diameter of that grain. Proportional to grain diameter. That can be written, that can also be written as d. So if we just wait. Okay, so the distance traveled by dislocation is directly proportional to the grain diameter d. So in this theory, one parameter assumed as x is written as the average distance traveled by dislocations. In a grain. So x can be written as the beta d, where beta is a constant. So in this, the strain in the grain is written as the rho bx, where rho is the dislocation density, b is Berger vector, and x is the average distance traveled by dislocation. So by putting the value of x, it is rho b beta d. So from this, the dislocation density can be written as the epsilon by the beta 1 by d. So again, if we put this term in the whole pitch relation, alpha g v square root of epsilon b beta 1 by d. So if we extract the 1 by d term in this term, that can be written as by assuming this in by k. So the whole patch relation from the work hardening theory also can be derived. So from this equation, as the rho is directly proportional to the strain, so if strain is increased, dislocation density will also increase. And in the initial method, in that if the dislocation diameter decreases, then dislocation density increases. So summary of the grain refinement mechanism is that the grain boundary strengthening can be done in two ways. First is the grain boundary dislocation pile up at the grain boundary. Second is the grain boundaries act as dislocation source. And third is the work hardening theory. So this was the mechanism related to the grain refinement. So by refining the grain size, the fracture strength of the material can also be improved. Fracture strength and toughness also improves with decrease in grain size, but the creep of the material, creep resistance will be low. Because the creep is dependent on the grain boundary sliding method. So if grain boundary area is large in the fine grain material, so due to the large grain boundary area, the sliding of the grain boundary sliding behavior will be high, and due to the grain boundary sliding, the creep resistance will decrease. With decrease in grain size. And the grain refinement also improves the surface finish after anodizing. So the three mechanisms was of grain refinement. The next is the grain refinement method. means how grains can be refined. So first method of grain refinement is the during melting and casting. So during the melting and casting, solidification behavior of the material is modified in a manner that lead to the decrease in grain size. So the solidification behavior can be modified by the nucleation method. So we know that the nucleation is two types. One is homogeneous and next is heterogeneous nucleation. So in the homogeneous nucleation, the nuclei of grains will form throughout the liquid region. While in heterogeneous nucleation, nuclei of grain is prefer the certain locations as the mold balls, certain sites such as mold balls. So the homogeneous and heterogeneous nucleation we will study in detail. So homogeneous distribution for the homogeneous nucleation, it starts if we assume a liquid and in which a solid nuclei will form in the liquid. So the solid nuclei will form without any aid of surface or defects. So for this solid nuclei, if we see the energy generated during the nucleation of this solid, so the one energy is associated with it, that is the volume free energy of the solid nuclei. Next is the surface energy of the nuclei. So the total energy delta G for this nuclei can be written as the delta GV into volume plus delta GS. So the curve between this, the total energy resulting from these two contribution of these two energies, volume free energy and surface energy, can be drawn as the, so this curve is for delta GS, that is 4 pi r square gamma the second curve is delta GV, that is 4 by 3 pi r cube into, and the resultant curve between, because of these two energies, it will be like this. So the initially the dominant term is the surface energy, as the surface, as the solid nuclei radius is solid nuclei of radius is very small, so surface area will be high. So the surface area term will dominate. As the radius increases and reaches a critical size, then after that critical size, the volume free energy term will be prevalent in this nucleation, and the solid nuclei will start to grow after only this point. So this can be referred as the R star, and the free energy associated with this R star will be delta G star. So if we so the delta GT term can be written as the 4 by 3 pi r cube delta GB plus 4 pi r square gamma. So if we differentiate this term with respect to radius, d delta GT by dr, and equate it to 0, so we will find the critical size of the solid nuclei, that will be minus 2 gamma by delta GB. And if we put this value in the total free energy term, then it will give the critical free energy required for the nucleation of solid nuclei, that will be 16 pi by 3 gamma square by delta GB cube. It will be cube and it will be square. So this is for the homogeneous nucleation. In heterogeneous nucleation, the probability of nucleation. Good evening, sir. Sir, are you taking this course? So in the heterogeneous nucleation, probability of nucleating the solid is much higher on certain preferred side. Like grain boundaries, mole walls, and dispersed particles. So the nuclei can also form on the inclusions, but on the intrinsic inclusion present in the melt, but that will reduce the ductility and toughness, because the presence of intrinsic inclusions will reduce the ductility of the material. That's why the heterogeneous nucleation on the intrinsic inclusions is not preferred. So as the surfaces for nucleation is more, so the nucleation number of nuclei will be high. Will increase. That will further increase the nucleation rate. So there are two terms. One is the nucleation rate, second is the growth rate. So in the solidification process, if nucleation rate dominates, then we will get the fine grain size, and if growth rate dominates, then we will get the coarse grains. So for the nucleation of aluminium grains on suspended particles, the foreign particle was added in the melt. The particles can be the metal powder or ceramic powders. So generally in aluminium alloys, titanium powder is added for the heterogeneous nucleation. So the titanium will react with the aluminium and form an intermetallic Al3Ti. The melting temperature of this intermetallic is very high, so it does not dissolve in the melt and provide a heterogeneous site. So for addition of titanium powder, in the titanium is not directly added in the alloy. The aluminum titanium master alloy, which has some specific composition, is added in the aluminum alloy melt, and the amount of this master alloy also depends on the concentration of aluminum which we will require in the matrix. So very small amount of this master alloy is used for generating the heterogeneous nucleation. So in the heterogeneous nucleation, the total free energy can be written as the delta GV into volume plus delta GS surface. So here delta GV is same as the homogeneous nucleation, that is 4 by 3 pi r cube into delta GV. But delta GS surface energy term will have some certain terms. So for those terms we will see one mechanism of nucleating a particle on the suspended particle surface. So if this is the solid nuclei formed on the suspended intermetallic, this is intermetallic surface, and this is liquid aluminium. So the contact angle between this is theta, and surface energy associated with these three surfaces will be gamma SL, gamma Li, and gamma Si. So for this the relation between gamma SL cos theta can be written as the gamma Si minus gamma Li. So from this, so because of this three types of surface energies associated in this case, the surface energy term is written as the ASL, gamma SL is area, and the surface energy associated with that surface area, AIS, gamma IS plus AIL, so it is minus AIL into gamma IL. That can be further written as the delta G heterogeneous equal to the gamma V delta GV plus A gamma SP, surface energy of the solid particle interface, multiplied by a angle term, that is 2 minus 3 cos theta plus cos cube theta divided by 4. So this term can be written as the S theta. So delta G, and this is same as the delta G homogeneous term. So delta G heterogeneous can be written as the delta G homogeneous multiplied by the S theta. So if we differentiate this equation also, we will get the critical nuclei size as the minus 2 gamma by delta GV. So it is same as the critical size required in the heterogeneous nucleation, but the critical free energy required for heterogeneous nucleation will be the 16 pi gamma cube by 3 delta GV square multiplied by the s theta term. So if we draw a curve between s theta and varying with the values of theta, this is 0, 90 degree and 180 degree. So at 90 degree the s theta value will be 0.5, and with at 180 it will be 1. So at 90 degree the value of s theta will be 0.5, and at 180 degree contact angle the heterogeneous nucleation free energy will be directly equal to homogeneous free energy required during homogeneous nucleation at 180 degree contact angle. Degree contact angle means it will be just this type of film at the solid particle interface. If we see the variation of delta G heterogeneous divided by delta G homogeneous with respect to s theta with respect to contact angle, so the curve will achieve 0.5 value at a 90 degree angle. So for the nucleation to start or solidification to start, the temperature should be temperature of the melt should be less than the melting point of the aluminum alloy. If we draw a diagram between free energy and temperature, so at Tm Gs Gl, so below Tm the free energy of Gs is less than the free energy of liquid, so the difference between Gs minus Gl will be negative, and the negative as the free energy decreases, the solidification the negative free energy value favors the for solidification to start. So only at temperature less than melting point, the delta G value will favor the solidification. So that the temperature difference between a temperature that is less than the melting temperature and Tm is referred as the undercooling. So the delta GV volume free energy term can also be written as in terms of heat of fusion for the alloy. So and the undercooling term. So delta HM is the heat of fusion, and delta will be undercooling. So in this heterogeneous nucleation, the R star is written as the 2 gamma by delta GB. So if we put this term, then R star will be minus 2 gamma by delta HM delta TM into TM. So the critical size of nucleus is inversely proportional to the undercooling. So as the if undercooling will be high, then critical radius required for the nuclei to grow will be low. So means for higher undercooling, high cooling rate is also required. So with high cooling rate, nucleation rate will be high, lead to fine grain size. So if the high cooling rate is done at from high temperature, rapid cooling technique for grain refinement during this, so the will provide the very high nucleation rate. So next first method is the solidification behavior modification. Next method is the mechanical vibration or agitation. So due to the mechanical vibration and agitation provided during the solidification process, breaks the growing dendrite, and those broken dendrite dendrites will act as the nuclei for the growth of for growth of different grains, and because of the increasing nucleation sites, the grain size will be refined. So the agitation can be provided by the gas purging, stirrer, or electromagnetic stirring. Third method is the melt inoculation. In melt inoculation, the grain refiner elements are added in the melt to solidify. So the grain refiners can be titanium, vanadium, niobium, boron, zirconium, and tungsten. And in these grain refiner elements, the titanium is the most effective element for the melt inoculation. So one alloy is the aluminum titanium master alloy for the melt inoculation. This is binary. One more master alloy is used, that is ternary aluminum titanium alloy, which has the boron also in this. So the addition of boron provide the additional surfaces during the solidification process by forming the two types of intermetallic. One is the aluminum Al3Ti and second is the TiB2. So this is more effective than the aluminum titanium. So for the melt nucleation to happen, different concentration of this master alloy is added to achieve the certain concentration of this titanium. So for the heterogeneous nucleation to start, the 0.01% of titanium in the melt is enough for the heterogeneous nucleation. If we use the aluminum 5% titanium and 1% boron, then the 0.2% of the ternary master alloy is required to add in the molten aluminum. If we require for the 0.01% titanium. If we want to increase the titanium concentration up to 0.05% titanium, then aluminum 5% titanium master alloy is required. Of 1% of this powder is required to add in the melt. And for the 0.01% titanium and 0.003% boron, the titanium boron ratio should be 5 and 3. This is commonly used. To achieve this concentration. And in this melt inoculation process, the reaction time and temperature also determines the efficiency of this heterogeneous nucleation. And cooling rate. That affect the morphology of intermetallic compounds forming during the process, during the reaction. Which is L3Ti and TiB2. So if rapid cooling is done from high temperature, then the petal-like aluminides will form. If slow cooling from high temperature is done, then plate-like morphology is obtained. If slow cooling done at low temperature, from low temperature, then blocky type of intermetallic particles are generates. So during the high temperature, acicular shape is obtained, and for low temperature, equiaxed particle is achieved. So the different morphologies of the intermetallic particles formed during the addition of master alloy defines the different interfacial energies provided by these intermetallic particles. So this morphology lead the interfacial has the different interfacial energies. And the particles which has the more providing more surfaces with less interfacial energy are good for the heterogeneous nucleation process. Energies are good, and the low interfacial energy also means the less low disk registry of planes between planes. Of intermetallic of particle and aluminium nucleus. So the Al3I intermetallic is the faceted type of particle. So in this number of facets are high. Compared to plate-like morphology. So in the melt inoculation, two mechanisms work. One is the carbide or boride theory. In which the titanium carbide and titanium boride forms. So the titanium carbide automatically forms during the inoculation process without any add of carbon. The only ppm level concentration is enough for the formation of titanium carbide. Concentration is enough to form titanium carbide. The aluminum boride can also be formed in this process. One more is the aluminum and titanium boride. So for the carbide and these carbide and borides, the interfacial energies between this is the gamma, liquid and solid. This is gamma LP, this is particle, and this is solid, gamma SP. So the gamma LP for the carbides and borides is very low. And gamma LP can be written as the gamma SP plus gamma SL cos theta. So for this alloy, this value is very low, and it is not a good inoculant. Because of the poor wettability. And the less means the and it also does not provide the load trace registry between the planes of particle and the alpha aluminum nuclei. the percent of this registry for aluminum boroid is around 5.2% between the 0001 plane of aluminum boroid and 111 planes of alpha aluminum. While for the titanium boroid, this registry is 5.9%, which is very high. So to avoid this carbide formation, the aluminum titanium boron master alloy is used. So because of the addition of this ternary master alloy, the Al3Ti intermetallic particle formed during the inoculation process that has the less disk registry and provide good wettability. Next theory is the peritectic reaction. Peritectic theory. So in this theory, the Al3I intermetallic present in the melt enables the formation of alpha titanium, alpha aluminum nucleus before the solver's temperature, that is 660 degrees Celsius, reaches. So the reaction can be written as the liquid plus Al3Ti gives alpha aluminum. So this reaction happens only at the 665 degrees Celsius. For the concentration of titanium, 0.15% titanium. So the limitation of the concentration and the temperature limits this peritectic theory mechanism. Means the 0.15% titanium addition is very high for the inoculation, and this reaction only occurs at this definite concentration and temperature 665 degrees Celsius. So to further modify this peritectic theory, the boron is also added that influence the peritectic reaction. And also cause a shift in composition. Means the alpha aluminum nuclei can also form for lower concentration of titanium. So the addition of boron leads to the reaction of alpha liquid gives alpha aluminum, plus aluminium titanium boride plus the Al3I precipitate also intermetallic. So the addition percent of the boron is limited up to 0.001% of boron, and titanium is 0.115% of titanium. So next reaction is written as the liquid plus Al3Ti plus titanium boride will give the alpha aluminium plus TiB2. But this registry for titanium boride is very high, that is 5.9%, while for Al3Ti is only 4% this registry between planes. So the 112 planes of Al3Ti and the 111 planes of alpha aluminium. So only 4% mismatch is there. So if we see the assignment of the week 7 lectures, in the first question it is asked that what is the critical size of nucleation in a homogeneous nucleation. So the dependence of the R star in the homogeneous nucleation is asked. So first answer is that is directly proportional to free energy. So this is wrong. Independent of free energy and directly proportional to surface energy, means R star can be written as the 2 gamma by delta G. So it is directly proportional to the surface energy. Next question is the critical nuclei radius R star is, so the first option is the minimum size needed for growth to continue. So this is correct. The maximum size up to which a grain can grow, this is wrong. The next, it is the same for both heterogeneous and homogeneous nucleation, so it is right. And the last option means it is higher for homogeneous nucleation compared to heterogeneous, is also wrong. So only A and C is correct. In the third question, the critical free energy delta G star for a heterogeneous nucleation is dash than for the homogeneous nucleation. So for the free energy required for heterogeneous nucleation is always lower as compared to homogeneous nucleation. So correct answer is B. In the fourth question, that is in a solidification experiment, an aluminium billet is heated to 700 degrees Celsius and to be cooled. Just wait. So we will start from the first question. So the critical size of nucleus in a homogeneous nucleation is directly proportional to surface tension. In the second question, it is asked that the critical nucleus radius R star is the minimum size needed for growth to continue, and the one more option is correct, that is the same for heterogeneous and homogeneous nucleation. In the third question, it is asked that the critical free energy for a heterogeneous nucleation is always lower than the homogeneous nucleation. In the fourth question, the aluminum billet is heated to 700 degrees Celsius and was undercooled. As the degree of undercooling increases, so because of the undercooling, means delta T is high, so solidification rate will be high. Or so first question is correct, and because of the high undercooling, the nucleation rate is also high. So the second option is also correct, means grain size becomes finer. In the next question, consider the following statements. Metals do not solidify exactly at the melting temperature. Second is the solidification occurs at a temperature slightly above the melting point. This is wrong. At melting point, the driving force is 0. This is correct. And the last statement is a negative delta G is necessary to drive the solidification. So this is also correct. So first, third and fourth is correct options. In the next question, it is asked that choose the curve representing the highest degree of undercooling. So in this graph, we can see that the critical radius required for the nucleation is different for all three curves. So the R star in one case is less than the R2 and R3. So the critical radius required for the solidification is low, means R star is written as the 2 gamma Tm by delta H into delta T. So R star is inversely proportional to undercooling. If R star is low, delta T will be high. So the question asked is which curve represents the higher degree of cooling. So the first option will be right. In the seventh question, nucleation in solids in most cases is governed by heterogeneous nucleation, because there is always secondary particles and mole surfaces provided for the nucleation. So the heterogeneous nucleation always dominate. In the eighth question, if the delta G star heterogeneous is given as the 10 kilojoule per mole and delta G star for homogeneous is given as 15 kilojoule per mole, then calculate the shape factor. So shape factor can be written as the ratio of delta T heterogeneous and the delta G homogeneous. So if we see as 10 by 15, so the correct option will be 0.667. In the ninth question, which of the following properties can be enhanced by grain refinement? So from the grain refinement, fatigue strength increased, fracture strength increased, and creep strength decreases. So only the B and C option is correct. In the 10th question, during heterogeneous nucleation, if the contact angle tends to 90 degree, they calculate the shape factor. So for 90 degree, the ratio, the heterogeneous nucleation shape factor will be 0.5. So in today's session we learnt about the grain refinement mechanism, which is dislocation pileup at grain boundaries, work hardening theory, and grain boundaries acting as a dislocation source. So there are three methods, and these are mechanisms. In the grain refinement method, first is the modification during solidification. By homogeneous and heterogeneous nucleation. Third is the mechanical agitation and stirring. Mechanical agitation. Third is the melt inoculation. In which suspended particles such as titanium and vanadium zirconium are added to form intermetallic compounds. Those intermetallic compounds will help in the heterogeneous nucleation. So this is all for today's session. Thank you.